Team, welcome back. Let's talk about electromagnetic fields. So electromagnetic fields are basically the relationship between electric fields and magnetic fields. If we change the magnetic field, it induces an electric field. If we change the electric field, it induces a magnetic field. We can see the relationship in this diagram right here and this graph right here, where it shows the propagation of an electromagnetic field as it's going through a vacuum. This vacuum right here represents, hey, a ray of light traveling to that vacuum. Let's put it that way. We can identify the direction because it is giving us, hey, the direction is going this way. Okay? The electric field and the magnetic field travel perpendicular to each other. So there is a method to how to identify the electric field and the magnetic field. We use the right-hand rule. If we know the direction of the magnetic field or the electromagnetic field, if we know the direction of the electromagnetic field, and this is the wave propagating in this direction, then also identifying the electric field pointing in the index direction, not index direction, with my index finger, and then using the magnetic field with my middle finger, the magnetic field should be pointing out of the page. So it should look something like this. This should be the diagram, how it looks like. So electric field is pointing with my index finger in this direction, and then my middle finger should be pointing out of the page. Okay, so that's how we identify the directions between electric field, magnetic fields, and the wave direction. Let's continue practicing this because this is important. Let's say that the magnetic field is going in this direction, so make sure that you put your middle finger pointing in that direction, your index finger pointing upwards, or up the page, and then where is your thumb pointing at? If you have your index finger pointing up of the page, your magnetic field pointing to the left of the page, your thumb should be pointing on out of the page. So let's do another practice. Let's say that we have identified the magnetic field and we have identified the direction of the wave. Now we have to identify the electric field. So this right here represents that it is pointing, your direction of the wave is pointing into the page. So if the thumb is pointing into the page and your electric field, not electric field, but your magnetic field with your middle finger is pointing down on the page, that means your electric field is creating in this direction, is being built in this direction. Okay? All right. Well, that's enough for right-hand rule for now. Let's talk about these two equations. So we saw these equations very similar when we were talking about the mechanical waves and how do we actually graph them. It is the same concept. It is a sinusoidal function, right? Just like we see in the graphs. And this symbol right here, these right here tell us the direction of the wave. So in this regard, for this graph right here that we see here, since the wave is going in this direction, the positive x direction, this means that if we're going to graph the electric field, it has to be negative. If we're going to graph the magnetic field, this sign also has to be negative. Okay? This, the E represents, the E naught and the B naught represents the peak electric field and the peak magnetic field. Basically, like what we see right here, those are the amplitudes of both waves. Another thing is the relationship that it has on the speed of light. It is just basically this equation right here describes that the relationship between the speed of light and the electromagnetic wave. If you have the electric field, the peak electric field, you can easily find the peak magnetic field and just substitute instead of having, and if you only have this equation, let's say, then all you have to do is basically find magnetic field, the peak magnetic field, substitute it, and you have the equation for the magnetic field. It's too easy. You don't have to change any of this part right here. You don't have to change any of this because it stays the same. Remember, it is basically the same wave but perpendicular to each other. That's why nothing really changes. But I want you to notice something important. Notice that here it's saying like EY and BZ. It is because it is already addressing that the wave is propagating in the X direction, right? Because it is propagating in the X direction, the electric field is propagating in the Y direction, and the magnetic field, it is propagating in the Z direction. Therefore, if it is changing, let's say that it is traveling in the Z direction, the electromagnetic field is traveling in the Z direction, these values, these letters change into something else. And you have to address that using your right-hand rule. And we will use an example of this in the next two problems. Okay, so covering that, now these two equations basically describe the strength of the electromagnetic wave. They represent the directional energy flux of the electromagnetic field. So these two equations are just describing that. I don't want to go too much into it. If you see something that is about wave strength, boom, you know exactly what they're talking about. All right. Now let's go to this example. 16.45. And this helps us in a way identify like the principles of what I was talking about, the right-hand rule. So in this one it's saying, hey, the wave is traveling in a vacuum. Fantastic. And it's traveling describing the following wave function. It's giving us an amplitude. This is E naught, or the amplitude. This is our angular frequency, and this is our phase angle. Here it is saying that, hey, the electric field is traveling in the Y direction, right? Because J represents the Y direction. But it gives us even more hints. It is also saying that the overall electromagnetic field, it is traveling in the X direction. Not only that, it is also describing us that, hey, it is a minus sign, so it is traveling in the positive X direction. Positive X direction. And the way that we identify where the magnetic field is traveling is by using the right-hand rule. So the thumb pointing in the positive X direction, the electric field using the index finger pointing upwards in the Y direction. Therefore, my middle finger should be pointing out of the page and in the Z direction. Okay, so we have that. Very good. Now let's go through the line. It says, hey, find me the amplitude. Well, we found the amplitude. It's E naught, right? And E naught is 5.00 volts per meter. That is big electric field. Hey, find me the frequency. Well, we already have the angular frequency, so we can solve for the frequency by just solving for the frequency. And it should be 9.55 times 10 to the negative, not negative 8, just 8. Easy there. All right. And then for C, find us the wavelength. So our wavelength, we can actually solve for it because it is going through a vacuum. The wave electromagnetic field is going through a vacuum, and therefore it is going at the speed of light. So if it is going at the speed of light, and the speed of light is 2.998 times 10 to the negative, no, not negative, just 8 meters per second, then we can just solve for the angular, no, not the angular, but the wavelength. And the wavelength should be 31.4 centimeters. Because we have the frequency comes from here, and the velocity comes from the speed of light. Done. We are done. So let's go to D. We already described that the direction of the travel of the wave is in the positive x direction. Positive x direction. Good on us, right? And then finally E. It says associated magnetic field wave. Remember what I said? Because we know the peak electric field, we can find the peak magnetic field. And the peak magnetic field is 1.67 times 10 to the negative 8 Tesla. And we can substitute that value with the rest of this equation. And be done with it. So instead of having E, we put B naught, and this will identify, and let me put K here, and it is K here because it is traveling in the Z direction. Remember that? Okay, and that's it. That's all you have to do. And that solves for the problem 16.45. Okay, so let's go to this one, and I'm not going to do the whole problem. I'm just going to do a section of it because I know like you're already like, all right, shut up. All right, I get it. But let's do this one partially. And I want us to practice the direction of it. It is saying, hey, the magnetic field is moving along the Z axis. The magnetic field of plane magnetic wave moving along the Z axis is saying that the wave is actually moving along the Z axis. So let's say that the wave, let's put it in green. The wave is traveling like this. Because I am putting this, because this is Y right here, and I identify Y because right here it gives me J, and it's saying that hey, the electromagnetic wave is traveling through the Z axis, but the magnetic field is traveling is propagating with the Y axis. Okay, so we have identified that. But one last thing. Notice too, now we have to identify the direction of the electric field. And look at the symbol right here. It is positive. Therefore, the wave direction, just like I put here, the wave direction is actually going in the negative direction. That means that if I use my right hand rule, I put my thumb in the negative Z direction, and the negative Z direction, and then I put my middle finger pointing out of the page. That means that my electric field is actually going downwards. So let's put it in blue. It's actually going downwards. So it is going downwards in the X direction. And notice that it's going opposite of the X, like the positive X direction. It starts opposite of the positive X direction. Therefore, E, when we first address it in this equation, let's put it here, E to the E, which is in the X direction. E naught is actually negative because it is going in the negative x direction. Okay? And then we can write the everything else here because everything else is the same. Let's just for posterity put the I there. Okay. And that's what I wanted to cover, just so you understand that how important it is to understand the wave direction, how important it is to understand the right-hand rule for the electromagnetic waves. I will leave this. You can see, look for the solution on your actual solutions page for electromagnetic wave lessons. But I'm moving on to the next class.